12 days of Qiskit. We're doing quantum error correction and we're doing it in a gamey way. Let's just get on with it now, shall we? So I shared in the chat a link. So if you want to follow along, you can follow that link. It's to some Jupyter notebooks that were the basis of some lectures that I did at the Quantum Error Correction Summer School, which was, well, it was in the summer of this year. But we're not going through them as lectures at the moment because this is 12 days of Qiskit. We don't do, I haven't got my hat on, have I? We don't do boring things like lectures. We're going to be looking at it in a more sort of interactive, gamified way. So let's go through this notebook, which is Dikadoku, Quantum Error Correction as a game. And if you haven't installed Qiskit QEC, which is the part of Qiskit that we're going to be using for this, you can install it using this line of code here. And this is actually going to install a specific branch on which we have the game that we're going to play. It's not been merged into main yet. And then all you have to do is import the game, and then you can move on to defining the game object. And it's all played on a graph. So here's a specific instance of this game. So I think the best thing that we can do is to start by taking a look at a sort of tutorial into what this game is. So let's open up the tutorial here. So yeah, this is the playing board. This is where the game is happening. It is a grid of these circles. We're going to call them nodes. They're connected by lines. We're going to call those edges. And these nodes can take one of two possible states. They can either be red, which is going to be viewed as being the off state, the 0 state. Also blue is the off state, it's the 0 state. And red is the on state, it's the 1 state. And when a game is being set up, then, oh, it seems that someone's asking for the link, and the link has disappeared. This YouTube chat seems to be a bit weird. And I guess maybe you only see the things from when you started watching. I don't know what it is. Anyway, I have put it in there again. So what was I saying? So we have this grid and the nodes are blue or they're red. And the way a game is set up is that you'll go, so the computer that is setting up the game goes through picking links, and when it finds a link, it turns it flips the state of the nodes either side of that link. So for example, in this case, this link that I'm trying to gesture with my mouse has been selected, and therefore these two either side have been flipped from blue to red, and that's why they're red. Similarly, this one here, which I'm gesturing with my mouse, oh, the mouse goes big. That one was selected, and therefore, again, the nodes flipped from blue to red. And then here, that one was also selected, so that one flipped from blue to red. So this is a very simple example, and it doesn't really demonstrate why this is a game, what's interesting about it. It just helps us to get started on the journey to knowing what is going on here. So here we have another example. So here it was which links were selected to create these red nodes. Well, obviously, it was that link there and that link there. But over here, it becomes a little bit more complicated. So probably it was this link here that caused those two to flip, and then this link here that caused those two to flip. Okay, let's move on to the next example. And here we have, obviously, it's going to be this link here that caused those two to flip, this link here that caused those two to flip, this link here that caused those two to flip. And then this one is a bit more ambiguous. So now I'm going to have to explain what these orange nodes are doing at the side. So these orange ones, they're also either blue or red. They have one of those two possible states. But as part of this game, We're not allowed to know what they are.
Hey, James, sorry to interrupt. That link didn't show up. Do you mind posting that again and I can share it in the description?
So here we've got a red node completely on its own in the middle of nowhere. What caused that? And we can deduce that it was probably this big long edge here that was selected, which flipped this one and also flipped this one. And so we have deduced that this node is going to be red and that one is going to be blue. And that's essentially a solution to this puzzle. Oh, no one sees the link. Maybe YouTube chat doesn't like links. Well, go to qiskit.it/decoders. So that's qisk.it, i.e. Qiskit, but with a dot in there somewhere, /decoders, and that should get you there. So, okay, what's next? So I should also actually give a little bit of context here. That whole being muted for a minute at the beginning completely messed with my flow, man. So what's the point of this game? So this is a game that's based on quantum error creation. And later on, we'll maybe start looking at how it's connected to quantum error creation. But what I'm wanting to do now is just introduce it as a game, and we'll play it a bit, and then we'll move from there. Okay. So, okay, now a link has been posted, and hopefully it's the right link. Everyone click on it and complain if it's not. Okay, so let's move on to the next example. Well, actually, I'm bored of examples. Let's play a game. So when we run it, we see it in this form. We've got these red nodes on the blue background, and we've got to clean them up. That's essentially what quantum error creation is about. We have errors in a quantum computer, they make a mess, we have some way to see what that mess is, and we have to go in there and clean it up. So what we do in this, and the graphics are obviously very simple because this is a Jupyter notebook based game, but what we do is click on a pair of these nodes, one after the other, and it will clean them up. So click on those, and we do them in the way that we think they were created. So they were created in pairs. We've got to try and get rid of them in those pairs too. So we clean those up, 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 and then we're left with this one at the end, and we think, well, probably that was connected to this weird orange one at the side, which in this case is represented by a big long line. So we do that, and we've cleaned it up. And now we can play another game. We can make it regenerate it. It can generate a new set of links, and we can have a look at how we think those should be paired up. And oh, this one is horrible. It's a lot of nodes that are on their own. So how can that even happen? In the examples that we've looked at, we didn't see any nodes that are on their own. Thank you, Quantum Error Correction Zoo, for telling me my flow is still there. So here's an example where you can see a node that is a bit on its own. And so we can think about how these come to be. Well, here it's quite easy. This link down here was probably selected, flipping those two nodes from blue to red. But what happened up here? There's no one link that can explain what is going on up here. Well, what could have happened is that we've got this link and this link. So this node in the middle is part of both of those links. So if you had this link, it would have flipped this one to red and this one to red. But if you then have this link as well, it flips this one back to blue and then this one to red. So when we see these nodes that are sort of in the middle of nowhere, it's not because, well, it's still because of the same process, but you've had more of these links being selected, which in quantum error correction actually correspond to errors. So what we could do is say, well, these two, that was probably a pair of these events that caused that. So let's sort of undo one and then undo the other, and then we've undone it. And maybe this pair of events happened there. Maybe that pair of events happened there. Those two we can do with each other. Those two we move a bit more slowly. This mess we just tidy away into that corner. We have this one in the middle of nowhere. Maybe it goes to that edge. Okay, it worked. It was touch and go there for a while, but it worked in the end. Yeah. So is there any more examples? Are there any more examples? So this one is where everything's a little bit more complicated. And this is the kind of example of what we really will see when we're playing this game. So yeah, as you can see that these nicely rendered graphs that we get when looking at these in code are turned into this rather simplistic looking game when we run it in a Jupyter notebook. But as you can see, it is the same thing. It's the same grid of mostly blue nodes, and these red ones translate into red ones. And the weirdest thing is that these orange ones that are connected all the way to a whole edge become a big long line. But, you know, I'm sure you can figure it out. That one's for later, maybe. Okay, so hopefully, how much have I explained this game? Does it make sense to anyone? So I'll play a few more games. Actually, I'll turn the noise down a bit. So this parameter p, when we define a game, is the probability that an edge is selected, essentially, and it also kind of defines the hardness of the puzzle. So if we turn this down, then we're going to get a lot less going on. And then when we go to clean it up, it's going to be a lot easier. So we can quite easily go through this and say, okay, it was probably this pair. I hope my mouse is nice and distinguishable for you. It was probably this pair. It was probably this pair and this pair. And we've cleaned it all up. And at the end, it tells us whether we're right or not. And whether we're right or not is just whether we've guessed the right thing about what those two orange nodes at the side are doing. So let's try another game. Well, that was easy. Let's try another game. Also easy. So when we have a very low probability of error, it's very easy to, so a low probability of these links being selected. It's very easy to clean them up. It becomes more difficult when we go back to what we had before, which is these things being the probability of error being higher. So in that case, you have more that you've got to deal with. So here I'm just basically playing a game in front of your eyes. So where do we go from here? So yeah, it's still mostly just a process of going through and trying to work out what's going on. So the way I play this, and I'm just going to play it as a game now. I'm going to forget about trying to teach anyone about quantum error correction for a bit. The way I play this is you've got to start with the easy bits, right? So here's a pair. It's pretty obviously a pair. So the link in between there is one of the ones that's important. It's caused these two to go from blue to red. And so we can think, okay, these two are probably paired up. And when we do that, it removes it because we've accounted for that. We know what's going on there, so it's removed it for us. We can forget about it. And this pair here, it's also pretty easy. And this sort of Tetris block here, that's a couple of pairs. Let's tidy those up. And this one here as well. And here, well, there's a few different things that could happen there, but there's always going to be, we can tidy up a couple of them, and then one of them's going to be left over. So that one's got to be, that's got to be associated with that node on the side over there. And this one as well. And these two probably go together. And then it becomes, what on earth is going on with that thing? And to be honest, it doesn't really matter, because either that thing contains an even number of nodes, or it contains an odd number of nodes. If it contains an even number of nodes, that means there is some way to pair them up and they all explain each other. What that explanation is, who knows? But there is a way that they can all just pair up with each other. If there is an odd number, there's always going to be one left over, and that one that's left over must pair with the boundary. And which boundary it's going to pair with? Well, that's the question. So let's see if there's an even or an odd number first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's an odd number. Now, I would think because that big horrible thing is stuck together and stuck to the edge on the left, then this should be something that's associated with that edge on the left. So if we look at some of the examples, for example, here we see this pair pairs up. You don't need to involve any of those edge nodes at all. This pair, that pairs up. You don't need to involve any of the edge nodes. This pair pairs up. You don't need to involve any of the edge nodes, but this one's left over. So to explain where that came from, the story of that explanation needs to involve one of those edge nodes. So you know that one of the edge nodes needs to be flipped. And which one's it going to be? It's obviously going to be this one because they're sitting right next to each other. It's not going to be that one because then this is just a very simple story of, well, this edge must have been involved and flipped them both. It's not going to be what it could have been this edge and 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 this one and that one all together. Now there's just a more complicated story, so we can kind of discount that. Here it's more ambiguous because like this node is closer to the edge on the right, but the whole horrible thing is kind of stuck to the edge on the left. So I would say that this means that we should probably just smush this whole big horrible thing together and smush it into the edge on the left, and that'll make it work. And we've got green and it says correction successful at the bottom, so we're all good. It seems like we made the right choice. We can try something else. So here we've also got a big smudgy horrible thing, so let's just squish that together and it disappears. Okay, that was good. Here we can, there's different ways you could have paired up those four, but the end result is we need to know what's happening with the edges, so it doesn't matter how we pair them up. So let's just squish them together and get rid of them. Squish those together and get rid of them. This is a very Tetris-y version. There's a lot of Tetris blocks here. Squish those together and then get rid of them. And we're just left with this guy. So, boom, we did it successfully. Okay, so, well, let's do another. And while I'm doing that, who wants to know how this is related to quantum error correction? Is that something that anyone cares about, or shall we just continue playing this sort of as a game? I suspect that's where we should go, but I'll open it up to the audience since this is a live stream. Okay, so we've got a lot of obvious pairs here, which are just explained in this. You know, when you find an obvious pair, they're easy to explain. It's just the link between them that has been selected as being one of the links that is going to flip its nodes. So we just go through and fix all those. Now we get to the bits that are a little bit more complicated. So this is one of these instances, as we saw in an example, where you need a couple of links to explain why they're not sitting next to each other. But, you know, that's fine. Let's do that. And here we've again got a big, horrible thing. And so we're going to smush it all together. And we're not really going to care too much about the explanation as to how that big, horrible thing came to be. Oops, that's not what I wanted to do. So smush it all together. And because there was an even number of nodes, that just disappears. And now we've got a couple of odd ones over on this side. So it's worth noting, actually, if we go back to this example, another way you could have explained these two nodes is not by it being the combination of this edge and this edge that were brought into that were used as a way of creating the puzzle. It could have also been this edge that goes out to the boundary and this edge. In that case, it's the edge on the boundary that serves as, the middle one that in the end doesn't get affected. So either way you explain it, the effect on the edge is the same. It doesn't get affected. But that's just another way of explaining this same thing. So sometimes you have multiple ways of explaining what's going on, but all that's important is its effect on the edges as to whether you win this game or you lose this game. And an interesting thing about that is that these two could actually be quite far apart. It could be, you could have a red node here and a red node all the way down the bottom, and they would still be explained by being connected via the edge by just two nodes. And that's exactly what we see here, actually. So these two, we can explain this pair by them being connected by 1, 2, 3, 4, 5 edges, or just by this one being connected to that one via the edge. And that's, what happened there. Okay, someone has asked how it's all related to quantum error correction. Good question. So let's go back to this sort of diagram, because these diagrams are exactly the kind of diagrams that you might generate when you're doing quantum error correction. So they're something that come up, a way of explaining what's going on in the quantum error correcting code. So there's actually, this is kind of an abstract version of what is called a decoding problem in quantum error correction. And there's a few different examples of things in quantum error correction that this could correspond to. So one of them, and probably maybe the most obvious, is the surface code. So the surface code is when you have a grid of qubits and you make multi-qubit measurements. So you're constantly going through that grid of qubits, making multi-qubit measurements. So where do the qubits live in this case? So you might think the qubits are the big colorful circles, but in this case, actually not. In the surface code, the qubits live on the edges. So for every edge here, you can think of a qubit living on that edge. Okay, so if the qubits are the edges, then what are the nodes? Well, the nodes are associated with measurements that you do of collections of qubits, typically 4. So around each node, there are 4 qubits. And so you do this 4-qubit measurement. So it's a measurement that acts on 4 qubits, but it gives you a binary outcome, a 0 or a 1. And you set up your qubit state such that it should always be in a state where all of these measurements will always output a 0. And if you ever come across a case where one of these measurements outputs a 1, then you know that something has gone wrong. And this is exactly how we do quantum error correction. We take many qubits that are susceptible to noise and we set them up in a state where we're going to make multi-qubit measurements, and we should know what in the ideal case, we know what the outcome of that measurement is going to be. And then if we see that it's something else, then that's a signature, that's a clue that errors have happened. And then with those clues, we can try and figure out what errors happened and what we have to do about it. So the way we figure out, so it's essentially like a little mystery we have to solve. And that's why I was inspired 6 years ago to turn it into a puzzle game. because we have these clues. We've got to figure out what happened, and we've got to figure out what to do about it. Yeah, so what else was I saying here? So I had a thought for a moment. Oh, so yeah, of course. Let's go back to something like this. So what does this represent when we think of it in terms of the surface code? It represents we've set up our qubits in this state where they should always output a 0 for all of these multi-qubit measurements. And then we measure all of these multi-qubit measurements. And whenever you see a node that's blue, it means that that measurement did indeed output a 0 and everything's fine. And whenever you see a node that's red, it means for that particular node, the outcome came out as 1. It came out as the wrong thing. And that means that something went wrong. Okay, so what went wrong? Well, if you're making a measurement of these 4 qubits and you see something's gone wrong, and you make a measurement of these 4 qubits and you see something's gone wrong, well, they overlap on 1 qubit. So this gives you a clue as to what's gone wrong. And it gives you a very strong indication of what's gone wrong. That qubit in the middle of those two has suffered an error. So when we go through these things, trying to come up with an explanation as to why these red nodes are red, what we are doing is trying to figure out which qubits have suffered an error. Although we have some of these cases where it's ambiguous, as I was discussing before. So here we could have had these 2 qubits here and here suffered an error, or this qubit and this qubit suffered an error. So which one is true? Well, for some cases, you don't actually have to have the specific knowledge of which specific qubits suffered an error. You just have to know the net effect of all of the errors that happened on some important piece of information. And that's what these boundary nodes are here to represent. Actually, what they represent is the information that you actually have stored in here. You've stored 1 qubit's worth of information in this whole big grid of qubits. And whether when you read out that information, it is as it should be, or it is the opposite of what it should be, is what's being represented by the boundary nodes here. So we're just trying to work out whether our stored information has been disturbed or not. So I see no more comments saying, I have no idea what you're saying. Please say it all in a completely different way. So that's good to know. But yeah, if you do have any questions, then obviously let me know, and then I can explain it a little bit more. And I think a good thing to do then is to, while I'm waiting to see if there's any comments, let's play another game. And in this game, we're going into it in the full and certain knowledge that this is actually an example of quantum error correction. So here we are. We have been given some information. We are running our quantum computer. It's spit out some information that is going to serve as clues as to what errors have just happened. And we need to solve those clues to figure out the important information about whether it's affected our stored information or not. So we have to straight away, this is happening unthinkable numbers of times a second. We've got to solve these puzzles. So let's get on with it. So here it seems that between these two outcomes that have told us that something's wrong, an error has happened. So by identifying that, we've corrected it. We've corrected it. It's gone. Either we've gone in there and whatever it flipped, we've flipped it back, or we've just accounted for it, in whatever we do next. So now we fix that and we fix that. There's kind of a lot of nice, obvious pairs. Okay, I said that, and then it became less obvious. So here the errors could have happened here and here. So the errors could have taken this path, or the errors could have taken this path. Which path did they take? What should we choose? As I said, doesn't really matter. So as long as we know that these two were somehow, they explain each other. The error was over there. It didn't affect the boundaries, which means that it didn't affect our stored information. So everything's okay. And here again, we've got, well, it's like is that like a Romulan warbird or something I'm seeing now? It created, there's 4 nodes. They don't need to invoke the boundary. We can all again just smush them together. Okay, I got it wrong. Well, this, so I think I did pretty well there. I think the algorithm I used, pairing the obvious pairs, was a pretty good algorithm. Evidently, it wasn't good enough. And this is always the way. I mean, it could be that enough errors happen, that horrible things occur, that nothing can be corrected. This happens when you have enough errors. So we will see even more of this if we crank up the errors even higher. So let's go up to sort of 0.25. Now there's going to be a huge load of, like, if we look at this version, but half of the nodes are red now. A lot of horribleness is going on. So what kind of type of problems would require this type of error correction? Well, before we jump into this horribleness, let's talk about that. What requires error correction? So if we want to do, like kind of the long-term view of quantum computing is to have fault tolerance. So it means that every operation in your quantum computation is perfect. And you cannot achieve that by just making the hardware ever better. Your hardware is always going to have some baseline amount of errors. So the only way to achieve effectively perfect everything is to perform quantum error correction. So we hope that in the near term, we'll find ways of mitigating for errors. So there's something called probabilistic error cancellation that we're looking into a lot at IBM that should be useful in the near term. But in the long term, you need quantum error correction. And with quantum error correction, you're always going to get problems like this, where you have loads of measurement results coming out and they give you clues as to what's happening. And you have to do this process of decoding to try and figure out what's going on. So I would say, what kind of problems require this? All the problems. But this kind of syndrome graph is kind of very surface codey. It's very typical of the surface code. But also, actually, if you had a real life surface code, you would have to take into account the fact that when you make the measurements can also have errors. They might lie to you. And so then you have the sort of 2 dimensions of the actual space of your code, but then a 3rd dimension that corresponds to time, and the space in which you have to try and figure out what's going on doesn't just try and work out what errors happened on qubits, but also when your measurements lied to you. So it needs to be a sort of 3-dimensional problem in general. So you could also think of this as a 1-dimensional code with time. But anyway, I'm getting too into the technicalities. So if you go to the link that we finally managed to share, then there's a couple of lectures. So that's like 3 hours worth of listening to me talk. But that is also where you can find out the information, some of this information in more detail, should you wish. Now let's go back to this horribleness. So there's a few obvious, well, I say obvious. The trouble with obvious things is they might still be wrong. Because like here, there's this little Tetris block, which is 4. Okay, we can somehow smush them all together. Here's another 4. We can smush them all together. These 2 are fairly isolated. And, well, that's there. Here we've got a big horrible mess that spans from one side to the other. There's not a lot you can do about that. I'm kind of tempted to go for them, and that makes me tempted to go for them, and that makes me tempted to go for them, and then maybe like that, and then maybe contract this big horrible mess to there, and then contract that. I'm actually surprised. I tried to do my best, but we're getting to the, with that many errors, you get to the point where even your best is not good enough. So here we're doing it, as if we're playing a game. But of course, that's not how we're going to do it for quantum computing. We're not going to have people sitting there receiving these games as the results come out of the quantum computer, solving them, and then sending them back. We are not fast enough or accurate enough to do that. We are going to be wanting to use algorithms. So if I move over to the notebook for lecture 1, no, it's not lecture 101, actually, it's lecture 3. Then we can go through some of the stuff where I have implemented an algorithm. So it's the same, this is exactly the same thing as we've looked at so far. But, well, there's a lecture in here, so there's a whole load of text and explanations and blah, blah, blah. But we're going to ignore all of that and just skip to the end where it all hopefully works. So all of those nodes that I skip past implement something called minimum weight perfect matching. So minimum weight perfect matching is well, you just try and find basically the minimum number of links, the minimum number of qubits that will connect these red nodes. You're trying to find the minimum explanation as to how this whole thing came to be. And that will then give you clues as to how they perhaps should be paired. So in this version, they're all colored different colors because the algorithm that we're trying to use has tried to solve this problem for us. So the algorithm has said, okay, these two green ones, it thinks they should be paired up, and those two other sort of green ones, I lack the color vocabulary. Is it olive? It's perhaps olive. These two, this one with the edge, and this one also with the edge. So the net effect on the edge is 0. And this one alone with the edge over there, which means that the edge gets flipped. So this is what the algorithm, minimum weight perfect matching, thinks is going on here. So when we have very hard examples, we can give that a go. So let's, for example, go up all the way up to, we were doing it on 0.25 before, weren't we, when things get really horrible. So here, yep, lit up like a Christmas tree, which is kind of relevant for the 12 days of Qiskit, I guess. There's a lot going on there, and you easily run into the, I don't have any problems with distinguishing colors, but even so, we're getting into the case where we've got so many colors that they are hard to distinguish. But this can give us a bit of a clue as to how we should try to fix this. That is not working. What's going on there? Oh, great. Another technical issue. So this should be implementing the game, and then we can use this as sort of a hint, because obviously there's a lot of horribleness there. But by having this algorithm that solves this minimization problem, that can go through and figure out what's going on, helps us a lot. Now, unfortunately, my fan is going crazy, and that is not going to be very helpful for you because I had to give up on the other microphone and go for the onboard microphone. Yeah, anyway. So, there are some different kinds of decoding problems, which is what I plan to go through tomorrow. So today I was going to do a few runs where we use the minimum weight perfect matching as our guide. But we seem to have gotten to the point when my computer doesn't want to run these games anymore. So let's do something a bit different. So I kind of started explaining how. So I mostly explained how this grid corresponds to what we get from what we call the surface code, and gave you a bit of hand wavy explanation as to how it corresponds to something to do with time. Let's look into that time aspect a little bit more here. So let's imagine a one-dimensional code now. So you've got just a line of qubits. So look at the line on the bottom, for example. Imagine that is your line of qubits. So each link is a qubit, and the node in between them corresponds to a two-body measurement. So you're comparing the two qubits either side. And in that comparison, there is two possible results, 0 and 1. And one of those results is the right one, the one they should be in. The other result is the wrong one, the one they shouldn't be in. And yeah, so that's a good thing. And then, yeah, somehow we're storing information in that, and that is associated with the ends. Let's not worry about that aspect too much at the moment. Let's just remember that's the point of the game. So here, let's say we measure them all, and they all tell us that everything's fine. So that's our first measurement result. Everything's fine. Okay, what happens when we measure them again? Because we have to keep on measuring them to see if any errors are occurring during our quantum computation. So imagine this second line as being the next time we measure them. And this third line is the next time we measure them. And this fourth line is the next time we measure them. So yeah, and so far everything's fine. And in this fifth time is the next time we measure them. And in this case, we see that a couple of them are red. So this qubit most likely has flipped, and there's something wrong. So we could immediately go in there and fix it, and that's why when we look at the next line, everything's fine. Or it could be that we just account for that. Okay, we've seen that these two things aren't as we expected them to be, but if we leave them like that, then that is now what we do expect them to be. So even if that result comes out again, it is now fine because we've already been surprised by the horribleness. Everything's good. So the next time, either way you want to think about it, the next time everything's good, and then the next time we see another error. That qubit must be a bit dodgy. It's showing us an error again. But also we've got one in the middle of nowhere. Now if we look at it the next time, so when we get pairs like this, that can, I won't go through the details of this, but that can demonstrate that what we're seeing is that we're getting basically the signature that our measurement has lied to us. So maybe if they pair up vertically, maybe there wasn't an error after all. Maybe that our measurements just lied to us. So this is how we can think of this thing as not just a surface code, but we can also think of it as this one-dimensional code, which is actually what we call a repetition code, but not just looking at one round of measurement results from that, but by looking at multiple sequential rounds. So one thing I was wondering about doing is, shall we try actually running this on a device and getting some results. And then maybe tomorrow, if they're ready, if they've finished running, then because there's queues, of course, a lot of people want to use our devices. Maybe we can actually do puzzles that are based on real data that have come out of a real device. So now, for some reason, my computer has stopped letting me play this game. It's a perfect time to look at how can we actually run these things. So what we do is we import IBM Q. That's how we get our devices. We're going to need to transpile it. This is where we take a circuit and make it so that it can actually run, is tailored to running on a device. And we're going to use also Qiskit QEC. So that's the part of Qiskit that we're developing at the moment that has everything quantum error creation in it. And one thing it has in it is repetition code circuit, which is designed exactly for creating these one-dimensional sort of proof of principle versions of quantum error creation. So let's import all those things. And then if you're wanting to use the devices, you have to load your account. So let's load our account. That always takes a little while because it's got to talk to the internet and say, hello, can I use my accounts? And then you choose your provider. Now, if you are a normal person with public access, you've probably only got one provider. So that's pretty easy to choose your provider. I have a few providers, so I can choose the one I want to choose. And I choose the one that's the fourth one down the list. I'm not going to show you my list of providers, but just know it's the fourth one down my list. And the device that I'm going to go for is Geneva. So this is one of our 27-qubit devices. We have quite a lot of 27-qubit devices. They're kind of the workhorse of the fleet at the moment. And they look like this. We have the qubits arrayed in this way. And also we see that these controlled knots are not very good. That's why they're a bit lighter. This qubit also being very light is not very good. So we might want to avoid those, or we might want to not avoid those to see what happens. So if we want to create an example of one of these repetition codes, then we have to figure out how we're going to do this. So here we've got effectively, let's zoom in a little bit. If we look along one of these things, so this is a qubit, and this is a measurement, and this is a qubit. So these measurements that we make, we actually use another qubit to facilitate those measurements. So in order to implement this code, we're going to have to find a line of qubits that go between ones that we're going to use for the actual storage of information and ones that facilitate these multi-qubit measurements. So that's basically the first thing that we are going to have to do if we want to run this code. So I know it's supposed to be live coding, but live coding is hard. So I am going to refer to where I did this before. So I did this before for a 7-qubit device, which are the ones that you have access to just publicly. And I chose a certain set of qubits to be my code qubits and a certain set of qubits to be the ones that facilitate the measurements, which I call link qubits here. So I used these ones, but they are not going to be relevant for what we're doing now because we're doing it on a 27-qubit device. So let's start off here. Our first code qubit is going to be qubit 0, and then let's kind of go around here. So our first auxiliary qubit is going to be 1, and then our second code qubit is going to be 2. So let's put those in here. So our first code qubit is 0, and our first auxiliary qubit is 1. Okay, so our second code qubit is 0, our second auxiliary is 3. Sorry, our second code qubit is 2, our second auxiliary is 3. So 2 and 3. And then we'll use 5 and 8 just by continuing along here. So maybe I will zoom in a little bit. Check if anyone's saying anything. 5 and 8, and then 11 and 14. Okay, 11 and 14. And then maybe I'll avoid this one. So I could drive on straight towards here into all this badness, but maybe I'll avoid that. So let's go up here instead. 13 and 12 as our next one. Sorry, I got the wrong tab there. 13 and 12. And then 15 and 18. 15 and 18. And then 21 and 23. 21 and 23. And then that's okay, 24 and oh, I was trying to avoid that 25, but if I want to make a big long line, I'm kind of stuck. So let's do now 24 and 25. And I think that's it. I think I can't go any further. So so that's 0 to 5, 11, 13, 15, 21 and 24. As I can, oh no, we can use 25 and 26. Because we actually have more code qubits than we do auxiliary qubits. So we end with a code qubit on 26. So now we've figured out where we're going to run this. What's the next thing? So I'm going to cheat. Let's get rid of lecture 1 and let's get rid of lecture 2. So the next thing to do is to transpile it. So, and actually the scheduling method doesn't matter. So, well, actually I've already imported transpile here, so we don't need that. But actually we've not created a repetition code circuit object. So we have these things in Qiskit QEC called repetition code circuit objects, and we define them by saying how many code qubits we have, which we can call D. So D in this case is just, well, it's a number of code qubits we have. It's the length of that. And we're also going to define how many rounds, the syndrome measurement rounds we want. So let's call that T, and we're just going to have it so T is the same as D. And then we have to tell these things to the repetition code circuit object. Yeah, so that gives us this object, which is going to hold all of the information that we need about this code. And that includes the circuit that gets run. So it has a circuit that encodes the value 0 and a circuit that encodes the value 1. Let's look at the code that circuit that encodes the value 0, and it looks like this. So I might need to zoom out a little bit. But here the code, so we've got code qubit 0 and 1, and then all of these operations are used as part of this measurement that we're doing. So link qubit 0 feels this controlled knot. It is part of this controlled knot, which is controlled on code qubit 0 and targeted on link qubit 0, and also one that's controlled on code qubit 1 and targeted on code qubit 1. And by this means this comparison value of code qubit 0 and 1 is moved over to link qubit 0, where you can then measure it. So this is the circuit. It's much better when you use the matplotlib version. Well, it's also very long because we're using 10 measurement rounds, so it's just repeating the whole thing 10 times. I think it might be better to go back up to the top. and just get rid of that cell. So we're going to take that circuit for that logical value, and then we're going to take the back end that we want to run it on, which is Geneva. And also we want to tell the device that which qubits in the circuit we want to be used as which qubit. So which qubits on the device we want to use. What am I trying to say? We want to say which qubits on the device should be used for which qubits in the circuit. We don't want the transpiler to try and figure it out itself. We want to be certain which qubits we are using. And so for that reason, we use this initial layouts. And so if we look at code dot, and then the circuit that we want, which is that one. And then if we look at the qubits attribute, we see the list of the qubits in the circuit. There's all of the link qubits and then all of the code qubits. And so if we create a list of the qubits on the device in that same order and pass it to this initial layout argument, then it tells the compiler what we want. So we just add this list of all the link qubits to cover these to the list of all the code qubits to cover them, and that transpiles our circuit. Oh yeah, I don't have the stuff installed to display that in a nice matplotlib way, but it doesn't matter because what we really want is to run it, and to do that you do backend.run and then the circuit that you want to run, and that gives you a job object, and that job object has a job ID, so job.job ID. So now we're running it, and it's got this job ID, and that job ID can then be used to retrieve the results later. So tomorrow, we'll see if that's finished and whether we did anything wrong and it gave an error, or whether it's something that we can actually use. And then maybe tomorrow we'll correct some errors from a real quantum computer. Either way, we'll look at some more complex and interesting decoding problems that come from some more exotic kinds of codes. But that is pretty much all for today. So thank you for listening. Oh, and I have to say things at the end. Oh yeah, I have to hype up tomorrow. Tomorrow is me, so I don't know if that's good or not. Also, don't forget to like and subscribe, classic YouTube things. And I'll see you then with a better microphone. Goodbye. I'll say goodbye. I don't know how I actually end this thing. I assume Paul's going to do that.